the videos that this guy does are pretty good. And you can just type in topic, and then he's called the organic chemistry tutor. If you're having issues with some topic in class, even previous topics, you could probably look it up, and he would have stuff there for you. So you guys can check that out. I got to go grab these off the copier. They're hot off the press. I'll be back in 20 seconds. Sorry about that. All right, so we're going to go over the PowerPoint. This is the PowerPoint right here. You can click that, and that is all the slides. And then you can follow along with these written notes. Those of you in here, you may want to pull up those notes. That way you can fill them out while I'm going over the information. Then tomorrow we'll discuss, actually, I think we actually get done with everything today. We did at least last period. So basically we are going to get Wednesday and Thursday and merge them. And then tomorrow we'll go through and I'll show you some videos and stuff like that. And then we're done with the week. And then you have How Stuff Works. Did we do a How Stuff Works last semester? No. So this How Stuff Works water. If you've ever wanted to hear the word water 170 times in 1 hour, this is the best way to do it. You'll see. But yeah, it's a pretty good video actually. But the guy he says water like real weird. So it may mess with some of you guys if you can't handle stuff very well. I can't handle it. All right. So up to this point, we've been talking about intramolecular forces. And apparently I might not have said this well enough in period 5-6 because somebody asked me at the end, like, what do you mean by this? So intramolecular forces, intra means within. So the bonds that we talked about, like the bonds between hydrogen and oxygen and water, those are intramolecular. Like 465 is not an interstate, it's an intrastate because it does not leave Indiana. 465 just goes around Indianapolis, that's an intrastate. So the term intra means within and inter means between. That makes sense? So 74, which goes from, whatever, East Coast to West Coast, that's an interstate because it goes through multiple states. 465, intrastate. And nobody calls it an interstate. If they go and get on the interstate because they don't know about it. But when we talk about the bonds between hydrogen and oxygen, those are intramolecular. So we've already done all of our topics on intramolecular. Now it's time for us to go to intermolecular. Okay. So there are 4 major types of intermolecular forces. Easily enough, they are ion dipole, which is a pretty strong type. Imagine water molecules being attracted to a sodium ion, or water molecules being attracted to a chloride ion. Whenever you put like salt into water, those sodium and chloride ions get pulled apart. That's ion dipole. You got to know what dipole is before you can understand what ion dipole is. That's why it's a little bit hard, but these are the 4. Hydrogen bonding is strong as well. Dipole-dipole attraction is also decently strong, but not as strong as hydrogen bonding. If you have hydrogen bonding, you actually also have dipole-dipole attraction. The weakest, and the thing that almost everything has, is called a London dispersion forces. That is the weakest. If you have dipole-dipole attraction, you have London dispersion forces. Now, another teacher may have talked to you about London dispersion forces. How many of you had the Rat King? Mr. Sue? How many of you are Skaglets? Who did you guys have? Miss Williams. Did she ever use the term van der Waals forces? Not that you remember. So, yeah. So their biology teachers may have talked about van der Waals forces. Those are a type of dispersion force. We are just going to call them dispersion forces. So if you've ever heard the term van der Waals, then you've heard a little bit about this before. So if we are looking at them by their relative strengths, dispersion are the weakest. If you've got dispersion, that's the only one that you could have, maybe. If you've got dipole-dipole, you also have dispersion. So dipole-dipole has even stronger intermolecular forces. Hydrogen bonding and ion dipole are pretty moderate with each other. Now again, here are those intramolecular forces we talked about. You can have the covalent bonds, like the ones between hydrogen, oxygen, and water, or you could have an ionic compound where you have a metal cation and a non-metal anion bonded together ionically, and that's where you have ion-ion. Those are the strongest. We talked about that in the past. We said that you could put salt right on a hot stove, and you won't be able to melt it even in your house. You won't be able to get the stove hot enough to melt it. So it's got like an 800 Celsius melting point or something like that. But if you take sugar and do the same thing, you're going to end up running your pan, right? Because that sugar will then break down, and you'll be able to break the bonds in that sugar, that you'll be able to break those covalent bonds by adding enough heat, and then you'll end up with basically carbon on your pan. All right, so now we have the strengths of each. So let's go with the simplest, London dispersion forces. You need me to move that picture? Yeah. London dispersion forces, these are the weakest. So basically, if you have electrons, you will have some type of London dispersion forces, right? So let's just take a look at what this would look like if we had big things. Like, for example, how do I reset this? Need to move you guys down to half. Reset. All right, so if we take a look, this balloon is going to, basically we would just want to get a charge on it. So imagine we have some negative charges there. We know that opposites attract, right? So the balloon's going to get stuck to the sweater. Now watch what happens whenever I bring it close to the wall. See the electrons moving away from the wall? If they move away enough, then that balloon can stick to the wall. But that's kind of what's going to cause London dispersion forces. You're going to have electrons, and when those electrons get closer to each other, they kind of move. They switch around a little bit. And they create what's called temporary dipoles. Let's see if there is a better dispersion forces. What, diagram? Is that what you would call that? So if we have, this is pretty good. So if we take a look here, basically what you have is these electrons moving, and they create what we call temporary dipoles. What does di mean? Two. Poles is basically talking about positive pole and negative pole. Well, as those electrons move around and you get these temporary dipoles, the negative can attract to the positive, and that's the London dispersion force. It's very weak, but it can happen. Basically, the electrons, if you have more electrons, then that means they can move around more, right? So you can have a bit of a stronger dipole. And that's the key to this. When we look at something, we can look at its number of electrons to determine, in a sense, how strong the dispersion forces are. That's not what I want to share. I want to share this. All right. So these are the only forces of attraction between nonpolar molecules. So again, we'll have to figure out if something is polar or nonpolar. Large nonpolar molecules may have substantial dispersion forces, resulting in relatively high boiling points. Well, that jumped out of nowhere. What do they mean, resulting in relatively high boiling points? How would dispersion forces be connected to boiling point? Well, what is a boiling point? From our thermodynamics lessons last semester, what's a boiling point? Yeah. Yeah, when it goes from liquid to gas. What's the difference between the particles in a gas versus particles in a liquid? They're more spread out. So how would dispersion forces be related to boiling point? Well, if you had higher dispersion forces, that means that you would be attracting each other more. If you're attracting each other more, it's harder to get you to spread out. So the more dispersion forces you have, the more energy it would take to break those attractive forces so that you could boil. Small nonpolar molecules have weak dispersion forces and exist almost exclusively as gases. There we go. So let's take a look at some of the organic compounds that we recently had. Here is methane, ethane, propane, butane, pentane, and then octane. Well, if we take a look, these boiling points are in Kelvin. So at 100 degrees or 100 Kelvin, methane boils, turns into a gas. If we take a look up here, it takes 400 Kelvin for octane. Since octane has more electrons, it's more massive, it's bigger, it has more dispersion forces. So it takes more energy to present it or to get the molecule's attractiveness away from it. Methane exists as a gas. So that is dispersion forces. You have electrons, you have dispersion forces. The more electrons you have, the more strong your dispersion forces are. All right. So let's take then a look at molecules such as HF. We know that this molecule is said to be polar. We look at the electronegativity difference, we would find it for HF to be higher than 0.4. What that means is that there's a partial negative charge on hydrogen and a partial negative charge on fluorine and a partial positive charge on hydrogen. Why? Because fluorine loves electrons so much, it's going to pull the electrons in this bond closer to it, which pulls it away from the hydrogen. Each bond is made up of how many electrons?
Two.
Two, right? So this is said to have a dipole moment versus a temporary dipole. The dipole moment is stronger. So when they have polarity and they have these dipole moments, there's an attraction between two sets of the same molecule or sets of different molecules with polarity. So the chlorine here is going to be attracted to the hydrogen here. That attractiveness has them holding on to each other more. There we go. And let's say you even take it further. What is the most electronegative thing on the board?
The fluorine.
Fluorine. Oxygen and nitrogen are right up there as well. NOF, NOF, right? NOF. If hydrogen, which only has one electron, if hydrogen is bonded to nitrogen, oxygen, or fluorine, then we have even something stronger occurring. We have what's known as hydrogen bonding. Hydrogen bonding is bonding between hydrogen and more electronegative atoms such as oxygen, nitrogen, or fluorine. This is actually what holds your DNA together. Here we have adenine and thymine. The hydrogen on thymine is bonded to a nitrogen. So that means that the nitrogen pulls the electrons away from it pretty well. This nitrogen here has an extra set of electrons that is going to retract to that hydrogen there. Same thing here. The hydrogen on this adenine is attached to a nitrogen. So the oxygen from the thymine is going to attract that hydrogen. We noticed that guanine and cytosine actually have 3 hydrogen bonds between them. It's said if you have more G and C in your DNA, it's more stable. What can come down through here and break this hydrogen bonding? What unzips the DNA? The teacher probably told you about
Helicase. DNA helicase.
it is helicase, right? So we know that DNA is a helix, and enzymes end in ASE, ACEs, right? What's the one in your mouth that breaks down starches? It's in your spit.
Amylase.
Amylase, right? You've heard of amylase probably. Once helicase comes down and breaks those hydrogen bonds and separates that DNA out, what are the catalysts that come in and replicate? What does it mean to build something? Do you remember? One goes 3 to 5 prime, and the other one, I don't
The
remember.
polymerase.
Yeah,
DNA polymerase.
Polymerase, Pol 1 and Pol 3, right? Polymerase 1 and polymerase 3. Those come in, yeah, right? But if it weren't for a helicase, the hydrogen bonding would stick the DNA together, and you could never break it into two strands and replicate it. I actually think that there is a cool video. Let's see if we can find it. Helicase. What would you call that? If you were watching this, helicase in action. Helicase in action. Oh. See, everything likes to do this. Let's watch video. It's a risky clip. I saw something. I saw one time that was mechanism that untwines DNA. 34 seconds, 5 minutes. Not worth it. All right. So that's hydrogen bonding. If you have hydrogen bonding, you have to have dipole-dipole because that's what a nitrogen, oxygen, or a fluorine attached to the hydrogen is going to be a dipole-dipole. And if you have electrons at all, you would have to have dispersion forces. So if you have hydrogen bonding, you have all the ones below it. If you have dipole-dipole, you have dispersion as well. If you are nonpolar, then all you can have is dispersion courses. Hydrogen bonding in water is pretty awesome. If we take a look here, again, the partial negative charge of the oxygen, partial positive charge of the hydrogens. This is going to attack the hydrogen here. It's going to be attracted to it. Water has a decently high boiling point of 100 degrees Celsius. This attraction here, if we take a look, that's why this first slide exists, because the water attracts itself so much that it creates a ball or a droplet, right? Does anybody know the term for that? Louder?
Surface tension?
What did you say? Cohesion.
Cohesion.
Yeah, surface tension was said in class, as well as cohesion. The surface tension is the amount of energy required to basically flatten that water out. When we say that water has high surface tension, it holds itself together because the energy required to flatten it out is high. Because we have to break all of these little hydrogen bonding interactions, right? And it takes energy, right, to break these. So the stronger your intermolecular forces, the higher your surface tension. Anybody know of anything that higher surface tension than water? What'd you say? More specifically, mercury. Yeah, mercury would have higher surface tension. So if we take a look, cohesion is the attractiveness of your particles to your particles, the same substances. Mercury, also very high surface tension, is not very attractive to other things. So when we talk about its meniscus, it actually has a meniscus going upward. That's cohesion, attracted to self. Adhesion. Adhesion is attracted to others. So if we take a look, not only does water have cohesion, but it's also attracted to glass and plastics. And that's why we get water crawling up the sides in a sense, making that downward meniscus. The only place that you probably ever be able to see a mercury meniscus is at the where. Yeah, if you have a mercury thermometer at home, it's possible. We don't have any more mercury here. But the best is that the doctor's office, if you look at the blood pressure gauge on the wall, that is usually filled with mercury. And you'll be able to see that what the meniscus we're not used to, those cohesion properties. Oh, yeah? Did you vacuum it all up? In a sink?
Wait, Mr. Jackson?
Yeah.
So the reason why like the meniscus is pointing up in adhesion is because the water is trying to get away, like the glass on the sides. That's why.
It's attracted to the glass on the sides as well. Yep.
Okay, thank you.
Yep. Actually, let's take a look. What are those things called? Water fountain. What's that gonna bring me anything? What is it called when you have that? Linear? Linear? No. Have you guys ever been to like Walt Disney World where the water shoots up and it holds itself together the whole time and then it like lands down here and you can see it?
Laminar flow.
What is it called?
Laminar flow.
Laminar. There we go. Who was that?
Gabe.
Nice. Yeah, laminar flow. So this is just like videos about people making these fountains. But if you've ever seen this, yeah, here we go. The jets in Detroit Airport. Give me an ad.
$9.99? No way. Wow.
Okay, check this out. I'm at the Detroit airport, which is pretty much like the future, and they have a laminar flow fountain that I love. How cool is this? Pop jets. There's my wife. Just letting me do my thing.
So there you have it, the laminar flow. Basically, that is due to the cohesion of the water and also some of the ways that it goes out. And you guys might know more about that if you're actually interested. You can probably talk to Gabe. Gabe, do you have one of these? Did you make one at home?
Nope.
Nope, not
I
yet.
just know it's called because all the science channels on YouTube won't shut up about it.
Are you serious? That's amazing.
Yeah, particularly that guy.
Oh, are you serious? That's amazing. I had no clue. But it is, I mean, it is cool. One last thing. I didn't want to switch that yet. Let's do this. Let's go back to it. This surface tension can also be not a good thing. This will work. So here's a guy skydiving, cliff diving. I don't know how to use YouTube apparently. But what I want you to see here, look at the water that he's going into. What's special about it? It's moving. They actually break the surface tension of the water by moving it and creating ripples and stuff like that in it so that it has less surface tension and the impact of whenever that person hits it. Another good thing about it is then they can actually see where it is, right? They can actually see where the water's coming up. It doesn't get lost in our minds like if you just see a bunch of water. And it gives them a visual reference. Yeah. He did it. Yeah, that's pretty cool. Yeah, yeah, there's still surface tension there, but it definitely reduces it. All right. Cuckoo. So we've talked a lot about boiling point and stuff like that. We need to talk about what's called volatile and vapor pressure. So the equilibrium vapor pressure is the pressure measured when the dynamic equilibrium exists between condensation and evaporation. So that's a lot of words. But what I want you to take from it is imagine that you knew somebody who had a dog and the dog died. And they had a water bowl for that dog. Eventually, what's going to happen to the water in that water bowl if they don't do anything about it? Yeah. It's going to evaporate. Even though the dead dog's not, licking up the water or anything, it will still disappear. Right? That's evaporation. So the opposite of evaporation is condensation. And we know if we have a glass of cold lemonade on a hot day, water from the air will condense on that colder glass. So vapor pressure, imagine if you had a dog bowl full of water and the pressure on the surface of that was so high that it did not just all evaporate away. But whatever would evaporate away would also condense. And this process would be dynamic because it's not the same water molecules each time. It's different, but they're ever changing. That's what it means to have dynamic equilibrium between condensation and evaporation. In order for this to occur, it will not occur at our 1 atmosphere planet pressure. But if we have higher pressure, it will keep those water molecules basically from floating or flying off the spot, right? So the idea here is that what is the vapor pressure required to keep that substance into liquid? And it's better to say at equilibrium. How many of you ever seen those lighters where you can see through it and you can see the liquid in there, right? That's reached vapor pressure. The pressure is high enough in there that it's keeping whatever the butane in liquid form. As soon as you release that pressure by pressing that button, what happens to the butane? It vaporizes and comes out, right? And when you stop, that pressure reforms again. That's vapor pressure. The more volatile a substance is, volatile is a word that basically just means that it doesn't have much attraction to itself. So it's going to spread out as much as it can, turn into a gaseous form. The more volatile something is, the higher the vapor pressure required to keep it in its liquid form. The less volatile it is, the less the vapor pressure needed to keep it in its liquid form. And I probably should not be saying keep it in its liquid form, but reach that equilibrium would probably be the better way to say it. The higher the pressure for something that's volatile to reach that equilibrium, the higher the vapor pressure, the more volatile it is. So it makes sense then, if something has a lower boiling point, it would require higher vapor pressure to keep it in that equilibrium. If something has very high boiling point, it's not very volatile, so you would not need much pressure above it to keep it at that equilibrium. And what is this all based around? Well, it's all based around the intermolecular forces. The greater the molecular force, the higher your boiling point is going to be, the lower the pressure above it to reach that equilibrium point. These are what we call colligative properties. These are properties that are determined by the number of particles dissolved in a solvent. Some of these you already probably know. You know freezing point depression. This is why we salt the roads in winter. The more moles of salt, the more moles of sodium and chloride particles in that solvent, the further the freezing point is depressed, which means it's less likely to freeze because the temperatures are not getting that low. Boiling point elevation. If we have salt water, we can get it up to a higher point of boiling than pure water. Again, this is because of these interactions. These particles in there are holding on to themselves, this ion dipole thing, right? The water molecules are holding on to the ions, and there's more attractive forces going on. So it takes more energy to get them to break these attractions. Osmotic pressure. How many of you have ever put salt on a snail or a slug? On leeches. If you've done that, you've used this osmotic pressure thing. Basically, what happens is the high concentration of salt on the outside forces solvent from the inside to go through their semi-permeable membrane. So basically, you desiccate them, you take out their moisture. Yeah, it turns them slimy, doesn't it? Like it's nasty. The last one is vapor pressure, which we've already talked about. So let's make sure we understand osmosis, and you guys have learned this in biology already, right? Osmosis, the flow of solvent into solution through the membrane. A semi-permeable membrane means that there are holes the size of which the solvent can go through, but not the solute. Did you guys actually have semi-permeable lab where you had like pig gut or something weird? No. Do they do labs in biology anymore? Or do they just let's cut up the pig? I'm videotaping this. You had one. You had one lab. Did you do the thing where you have like a piece of potato and then you let like food coloring go through it or something? Same idea, right? Yeah. So if we take a look here, here is pure solvent and here is the solution. So this has ions and the solvent, and this has just the pure solvent. And basically this is at 0.0, right? So what's going to happen here is solvent is going to come through that membrane. When it does, we have now more over here than over here. Well, if we remember our manometers from last semester, you guys know the manometer. Remember we measured the distance between this level and this level, and that gives us the pressure, right? So basically this level is higher, which means it's going against gravity, right? So there, that difference there, that is the pressure that we would have to apply to get them back to level. And that's what we call osmotic pressure. And here's the problem with the snail or the leech or whatever. Yeah, it's like snails are kind of cute, aren't they? Or maybe just cartoon ones are. But snails or leeches or slugs, if you put that salt on their body, atmospheric pressure is not going to be able to prevent that liquid from coming out of that semi-permeable membrane. Right? And that basically, that means that their insides are going to go out of them, which is not good for the snail or whatever, right? So that's the thing. That's like, if we lived on a planet with higher pressure, then maybe, but the amount of salt that people put on these things is kind of ridiculous, right? Did we watch that kid that blew up that glow stick last year? Yeah, okay. I just want to make sure that I was comfortable showing that because there's some cuss words in that one. I want you guys to, let me see if this even has it. Slug. What's that? Yeah. Not to even say all over your precious shirt. So there are some yeah, I don't think any of these are going to be good. I haven't pre-showed them. Yeah. So there are people out there that you can look this up on your own, I think, but they basically make a maze out of salt. And then they put a snail in the middle of it, which is basically like, I mean, snails are animals, so this is cruelty to animals. But luckily for the snail, they do have some receptors and stuff like that that kind of allow them to get out. But this is like jigsaw for a snail, right? Like, hello, slug. You ever seen that movie? We'll play a game today or whatever. Yeah, right. You've been slugging around these parts too long. But I mean, it really is just like Jigsaw or the Saw movie, Poor Slug. All right. Cuckoo. Let us share this then. You see that? So you've probably already filled out this whole front part, right? You got boiling point down. Who gave us the definition of boiling point? Boiling point is the point whenever it goes, isn't that you? Yeah. Yeah, we got all these.
Wait, Mr. Jackson,
Yeah.
Could you define vapor pressure again?
Yep, and it's a weird one. So you're gonna make me put it in words. Isn't there a slide with it in the words? I'm just gonna describe it to you so you have the idea of what it is versus some just generic definition. But if we have a lighter, right, or some type of container, Fido's dog bowl, and we have a liquid in there, right? Some of that liquid will evaporate, some of that liquid will condense. With me? The
Yeah.
more volatile liquid that is, it's hard to equal this equilibrium because even water will completely evaporate if you let that dog bowl out. So once these are equal, whatever the pressure up here is on the surface of that liquid, that allows for equality in condensation and vaporization. That's what vapor pressure is. It's what the pressure on the surface of that would be required to maintain equilibrium so that the same amount that evaporated condensed all the time.
So basically, the vapor pressure, because the water has a tendency to evaporate. So basically, once the vapor pressure reaches a certain point, it'll become equal rates. Both
You got it.
processes.
Yep.
Okay.
The evaporation and the condensation will be equal rate, equal amounts. All right. So the biggest questions for these type of things is, which one of these has the bigger boiling point? Which one does this? What does that, right? So if we take a look in samples such as each of the following indicate the strongest intermolecular force that can occur for it. So if we take a look, neon. It has electrons. So what can happen to it? Can it do hydrogen bonding?
No.
No. Can it do dipole-dipole interactions?
No.
No. Can it do dispersion forces?
Yeah.
Yeah. So London dispersion forces or just dispersion? How about iodine? What's the electronegativity difference here?
0.
0. So what does that mean?
Then it's non-polar, so you're gonna have London dispersion.
Yeah, right. It's nonpolar, so it can only have London dispersion forces. How about nitrogen trihydride or what we would call ammonia?
Isn't that polar?
It is polar.
So wouldn't that be like dipole-dipole?
Dipole-dipole, is it the strongest though? What's that hydrogen bonded to?
Yeah, it's hydrogen.
Yeah, right. The hydrogen is bonded to a nitrogen, so that's a NOF, NOF. So this can have hydrogen bonding. HP, baby. How about CO2? What's the electronegativity difference on those? You guys don't have your periodic tables out. Electronegativity difference. One. So are these bonds polar? Yeah, right. It's between 0.4 and 2. Is the molecule polar? No, because they cancel each other out. Yeah, the only way that you can do this is if you remember how to do the polar, non-polar stuff, right? If it's non-polar, what's the only type it can have?
London dispersion.
LD, London dispersion force. Right, right. The molar mass of 2 carbon compounds are listed below with their boiling points. Explain the large difference in these boiling points. So we have a boiling point of 338 and 184. Let's see, C2H6. What does it have?
It just has London dispersion since it's non-polar.
LD only. And we have CH3OH. Look at the masses. The masses, but this one would have definitely more electrons. But the more electrons, is that going to be enough to say, okay, it's over 100 and some more boiling point though? That's quite a bit difference between them. So what's the other thing keeping these molecules in methanol together? That would be hydrogen bonding. That hydrogen bonding, pulling those together, requires a lot more energy than it takes to get the ethanes to basically boil. When a solid lead piece is dropped in a pool of molten lead, will the solid sink or float? Solids or liquids, which ones usually have tighter packed particles?
Solids.
Solids, right? So what does that mean if the particles are tighter packed? Will they be more dense or less dense?
More.
So the lead will sink because the solid is more dense. All right, I think I'm gonna let you guys finish up this page down to 10. That's a good start. That's all I got for today, guys. Whew. Go ahead and finish down to 10. We'll continue on this tomorrow. I'll show you a few videos, and then we'll finish this up. And then Monday you'll watch how water works. And if you want, you can count how many times it says water in it. Like 170 times. He says it weird too. That's gonna annoy some of you. It's gonna be like, the only thing that water can do is water. Water, water. Sounds like one of those Philadelphians going, I want a water ice. Have a great day. If you have questions, always you can stay around and ask, but that's what I got.
Mr. Jackson,
Hey, what's up?
did you go over ion diploid forces?
Briefly.
Where was it?
About 'em.
Wait, what'd you say?
So what do you want to know about them?
Well, I never heard you explain them, so I was just
So here's an ionic compound right here. You see that?
yeah.
Yeah. Here's a water molecule right here. So what will happen is this water molecule will attach to one of these ions and it will pull that off. And it has an ion dipole attraction.
And a lot of things, like the things on the sheet, can we just Google them to look them up?
Yeah, by all means. We're not turning this sheet in anyway. This is just for your notes. Plus you have access. Yeah, you have access to the PowerPoints there as well.
I'm a little confused. Okay, so you said neon could not be hydrogen bonding, and why is that?
Well, is there any hydrogen when you just have neon?
No,
You need hydrogen for hydrogen bonding.
right? So if it has hydrogen, will it always be hydrogen bonding?
Nope, only if the hydrogen that you're talking about is bonded to an N, O, or F.
Okay. So like SO2 will not be hydrogen bonding.
SO2 cannot be hydrogen bonding because there is no hydrogen.
All right. Oh
Then
wait. Oh.
basically, at that point, you just got to look at its Lewis structure and determine if it is polar or nonpolar. And if it's nonpolar, then all you're going to get is dispersion forces. If it's polar, then you'll have dipole-dipole.
Okay. Well, thank you.
Hey, you're welcome. Have a great day.
You too.
Well, I mean, you do know that, like that's what the amusement thing is. Like, you know, whenever you're like in the bath or whatever, you get those things fingers. You're having some transfer of liquid. Yeah. So if you just dump it even like a bathtub full of salt after like I don't know 6 years. Yeah. Right. That's like some seven stuff or something like that. Is that what it is? Have a great day, guys. Okay, you were the one that, I did, are you okay? Yeah. And I'm gonna reopen it for you tonight? Yes. Yeah. Fine. What's the last name? Montgomery. Montgomery. All right, Noah.